standard deviation of 10. 280,000, standard deviation of 10,000. Actually, this standardization thinks that it's okay to say 280 and 10, if you want. We don't have to use all the zeros. We can just skip the zeros and work with the other scale. Then we could get different questions here. What is the probability that some randomly selected teacher earns more than 300,000? Or we could put it in more straightforward language and say, how large a proportion of these people earns more than 300,000 according to this model of what is going on? So probabilities are linked with proportions of how often things happen, or in this case, how many people are there of that type, right? The probability mathematically is like this. Then if we want to put it like this, we have this normal distribution with this mu and this sigma. That's the way we could write it formally. Then we could say, what is the probability of going above 300? We could use this standardization manual way of doing it and saying, well, I can subtract the mean and divide by the standard deviation to transform the probability statement to something on the standardized normal scale. And then I can recognize the question as the same question that I solved some minutes ago, that it's 2.3% to go below 2 standard deviations, either above or below, in this case above the mean. That would be one way of answering this question. So around 2.3% of the teachers have this salary above 300 here, right? We could also, and I'm showing it to you here instead of jumping into R, although it's slightly not well made. This way would be to call the p-norm, which by definition uses the standard version. I call it with 300 minus 280 divided by 10, which was the 2 I found from before on the standardized scale. This is why I'm saying maybe we could just skip all this standardization thing by hand, because of course that is built into the R function, that we can tell the R function to use the mean 280, use standard deviation 10. The M and the S are the R names for mean and standard deviation in the normal call, and then find the probability to be below or equal to 300 using those mu's and sigma squared, and that would give me the same answer, right? What about we have another group of teachers with a higher mean income, but also a smaller spread? What is the probability of the same thing? How many of those guys earns more than 300,000? Well, let us skip all the details and jump right into the R and say, what is the probability of going above 300, in this case, using the larger mean? So in a first thought you might think there would be more of these guys earning more than 300 because they have a larger mean, but of course I made the little point here that I also squeezed the scale such that actually among these guys there are much fewer having this high, relatively high, pretty undecent salary. Here's a more difficult one. What if I was a bit nasty, and sometimes we have been, if you check the exercises we've given you. What about if I sort of put the question the other way around somehow? I say, even though it's not unique, but give the salary interval covering 95%. That means I have to somehow go back. I go from the probability to the points and not from the points to the probability, which I just did before. Then we have the opposite function. The Q norm is the quantile function, right? P norm is this sigmoid probability function going from 0 to 1. The Q norm is the inverse of that, going from a probability to the quantile. That's why it's called Q norm. It's the same quantile name as we were taught 2 weeks ago. that when we were taught to find a quantile based on some numbers, for instance, the median or the upper quartile, these were quantiles. Now I'm finding a quantile in a normal distribution by taking the inverse of the probability distribution function. I don't have to think about that. I can just tell R to say, give me the points. I can tell R, give me the point where I have 2.5% and where I have 97.5%. Tell me what these numbers are in this normal distribution with the mean 290 and this one. And the way I put the question, there could be other choices, but now I choose the one with 2.5% in each tail. These are 282 and 298 when I do the rounding. Plus minus 2 standard deviations, basically. That was, that actually was this example as far as I would take it. You have to play around with it yourself. So we jump